Okay, so we're happy to have Guy Blanc from Stanford and working, I guess, learning and complexity, and will tell us about connections between the two.
Thanks, Avi. Does it matter where I stand? I know there's a video. Is this good? Anywhere's fine. Anywhere's good. Okay. Yeah, thanks for having me. I'm Guy. This is joint work with some excellent collaborators. Alex, at the time of doing this, was a master's student at Stanford, currently in industry. Caleb, another PhD student at Stanford, and Liang, our advisor. Okay, so I know this audience can sometimes be more math, more computer science theory. Feel free to slow me down at any point and ask questions. I aim for about 45 to 50 minutes for me to speak, and so there should hopefully be time for questions. I'm happy to take more offline if needed, but just slow me as needed. So this talk is about two seemingly unrelated concepts, both in computer science theory. The first is boosting and learning with lots of important applications, both in theory and practice. And the second is hardness amplification, which is a key ingredient in some complexity theory results. So I'll tell you a little bit about each. Okay, we'll start with boosting. The idea of boosting is to take something we call a weak learning algorithm and convert it into a strong learning algorithm. So a weak learning algorithm is required to output a hypothesis with slightly non-trivial accuracy. We'll go over this a little bit more in the next slide, but 50% is essentially trivial, so 51% is slightly better than that. And we convert this into a strong hypothesis, which gets high accuracy, something close to 100%. Okay. And the way this works, and the formal setup we'll stick to here, is the goal is to learn some unknown Boolean function. We have the simplest setting where we'll just say the domain is just 0, 1 to the n, and we get random samples, each drawn uniformly from this domain. So x is uniform from 0, 1 to the n, and then we get also a label for each point, labeled by our unknown function f.
You're not considering arbitrary distribution?
They will come up a little bit, but throughout this talk, the goal is to strong learn on the uniform distribution, and then we'll consider the distribution we have to weak learn over. But yeah, it's much easier to define smooth boosting over the uniform distribution, though there are analogs to other distributions.
Yeah, I guess the challenge initially was boosting before they knew how to do it, but to do it in the fact model for any distribution. But anyway,
yes, yeah. So yeah, we will see some changes in the distribution, but for now, think uniform. Okay, so weak learning algorithm takes these samples and outputs something that on a new point, a new x drawn from the uniform distribution gets 51% accuracy. Of course, the constant 0 or constant 1 function is always 50%. So this is the first non-trivial thing. Okay, so now we want to convert this to a strong learn on the uniform distribution. And the original version of boosting, the way it works is you assume you have access to a weak learner on any distribution. Okay, so D is any distribution on 0, 1 to the n. And we have an algorithm that meets the criteria at the top half of this slide, regardless of what D is. And then we're going to simulate this algorithm multiple times in order to create a strong learner. For the purposes of this talk, a strong learner on the uniform distribution. Okay, so the way this works, roughly speaking, is the learner starts with a guess distribution. It starts with the uniform. Every time it gets a weak hypothesis, it updates what seem like the difficult portions of the domain, and then it combines all the signals it gets from all these weak learners. Roughly speaking, it takes the majority of all its weak learning hypotheses into one capital H that gets 99% accuracy on the uniform distribution. And this idea has been around for many decades. When I took Intro to Machine Learning, I coded this up. So I think it's used in practice based on what we did in that class. And in theory, it has a lot of applications as well. Okay, so two downsides of boosting as I presented in the previous slide. The first is kind of definitional, which is even if we just want to learn on the uniform distribution, just want to strong learn on it, which by the way, we have a lot of nice techniques for handling the uniform distribution. We need a weak learning algorithm that succeeds on all distributions. So we've simultaneously made our task easier and harder, right? Easier because we need less accuracy, but harder because now we need to work on all distributions. The second, and this falls out from the first one, is it turns out that this standard version of boosting tends to not be robust. You can take a robust weak learner and it won't typically output a robust strong learner. And for this, let me say a little bit about one way of defining robustness, which is quite common, which is you have an adversary that can corrupt, say, 1% of your sample, and you still want to learn something useful. And what's going to happen during boosting is you're upweighting the portions of the domain that you think are hard. And so you're going to tend to upweight the points the adversary added. And so you're going to end up, instead of a 1% corruption, with a much higher fraction of your sample corrupted, and then things won't be possible. Okay, so to handle both of these, there were a series of works kind of implicitly defined, starting with Freund in 95, and explicitly named and defined by Servideo in 93 or 2003, which we call smooth boosting. And here we require less of our weak learner. We only require it to learn when the distribution is smooth. So let me tell you what that means. Roughly speaking, a smooth distribution is uniform over a large portion of the domain. And I'm just giving an explicit constant here, but what it means is there is some constant such that the mass on any point is within that multiplicative factor of the mass of the uniform distribution. By the way, to answer Avi's question earlier, if you can define this for not uniform distributions, but you have to change this definition. Like what it means to be smooth depends on the base distribution.
That's not what I meant. I was not talking about. I just said that the initial boosting challenge was for all distributions.
Yes.
Even the starting point. But can you boost something which is weak learner for any distribution, and then you want a slow learner for any.
Yeah, that's true. Okay.
So this is a mean entropy condition.
Yes. If the base distribution is uniform, this is just high min entropy within like an additive constant for the min entropy of what the uniform distribution is. Okay, so here we're now requiring less of our weak learners. Maybe it's easier to build these weak learners, which imply a strong learner, and they can also boost robust learners as well. Okay, so this is what smooth boosting. This talk, by the way, we kind of give two results, one in learning, one in complexity. I'm going to present them, start with learning, and then we'll start to do complexity. So here's our learning question, which is, what is the sample complexity overhead of smooth boosting? Okay, so let me tell you a little bit about what happens with existing smooth boosters so we can get into our results. With existing smooth boosters, you start with some weak learner that gets, now I'm going to kind of tell you, add additional parameter, it gets 1/2 plus gamma accurate using M samples. So gamma represents your advantage over a trivial learner. And what these algorithms do is they call the weak learner multiple times, and this requires more samples. And so they construct a strong learner using M over gamma squared samples. So depending on how much your original advantage is, you then need an appropriate amount of additional samples. Okay, so you could ask, what is the correct info? Yeah, go ahead.
Right. Can I ask, presumably this would be in some of those papers you mentioned, but do you know, could you say an example like of a problem where we can get a weak learner for these smooth distributions, but it's not known how to get a learner for arbitrary distributions?
That's a good question. It's probably easy to construct artificial ones. For natural ones, I think the robustness one is more. I don't know. So the uniform distribution specific techniques are often Fourier-based, and those don't necessarily extend to smooth distributions. But for the robustness side of things, then there are kind of black box results you can use smooth boosting for. Another application we'll see later is to the hardcore theorem, but I don't know off the top of my head like a concept class for which smooth distributions for not robust learning is easy. Yeah, good question. Okay. Okay, so what is the sample complexity overhead of smooth boosting? We have this upper bound, 1/gamma squared multiplicative overhead slices. It turns out there's a pretty easy lower bound of 1/gamma. The concept class consisting of all functions satisfies this, and you can only memorize, and for memorization, it's pretty easy to see that 1/gamma is the optimal thing. And our first main result is that up to, I think, a single log factor, smooth boosting requires an overhead of 1/gamma squared. And by the way, this is a separation against regular boosting, where you can show that 1/gamma is tight to regular boosting. And there's an interesting open problem here at the end that I'll bring.
What's the regular boosting?
If you require the weak learner to work on all distributions, then the sample complexity of weak learning can go up. And so 1/gamma is the right overhead to compare weak learning on all distributions versus strong learning on all distributions. And that's DC theory is how you prove this 1/gamma. Okay, so formally our first main result is the existence of a concept class. So there is a concept class with the property that if you want to weak learn it to 1/2 plus gamma accuracy, you need.
Can you go back?
Yes, of course.
Don't worry about time. We will ask questions and don't worry.
I like questions. That's great.
Don't you need one over gamma squared factor just to distinguish somehow, even if you wanted constant probability? Just to distinguish whether you have a weak learner or you have a random, you have a weak learner or you have somebody skewing random bit.
Good. Okay, so this is a very good question. So there are different results in the tightness of boosting. I think this distinguishing is related to the number of rounds you need to call your weak learner is always going to be 1 over gamma squared, just because, as you say, to distinguish. Theoretically, you could do something where you reuse your samples across the different rounds. Something like this could work. The result here is just sample complexity. It actually has nothing to do with the way you use your weak learner. This 1 over gamma says that if there is a way to get 1/2 plus gamma accuracy using M samples, then there is a way, it's brute force empirical risk minimization to get M over gamma strong learning. If you're calling the weak learner, you're going to need at least 1 over gamma squared rounds, but maybe you can reuse samples in a smart way. And this says information theoretically you can. Does that answer?
Well, a little bit, because I don't quite understand the model that says, you told us with M samples, you get half plus gamma. With M minus 1 samples, you don't get anything. Is this what you use in the law? We agreed that you need 1 over gamma squared rounds or accesses to.
Yeah.
If you assume that M is when you get information at M minus 1, you don't get any, there'll be a factor of M.
Yeah. M is the smallest number such that you get gamma advantage. M minus 1 might not be 0, it might be some other gamma.
But it should be used in the lower bound.
The next slide will give like a formal statement of you're talking about the lower bound of this 1 over gamma squared?
Yeah.
Okay, yeah. So the next slide will be like there's a concept class with certain properties. And feel free to ask more, of course. Okay, so there's a concept class such that in order to get 1/2 plus gamma accuracy, you can get 1/2 plus gamma accuracy with M samples over all smooth distributions. However, in order to get 99% accuracy, you need M over gamma squared, even over just the uniform distribution. Does this answer the, okay, yeah. And one thing to emphasize here, and this is also related to the discussion we just had, is that this makes no assumptions about how you call the weak learner, right? This says like kind of no matter what a boosting algorithm does, it can look at its own sample, it can call the weak learner, an inefficient number of times, and call it exponentially many times. You're still going to need a 1 over gamma squared sample complexity overhead.
This is for all M, you can construct such a class, or there's some constant M per way?
For all M, but the number of bits of the concept class is going to depend on M.
Sure.
Yeah, I need to look back at the exact parameters for all M. Yeah. Okay. That is actually all I'm going to say about boosting until near the end of the talk. For technical reasons, the proof for boosting starts with the proof for the hardcore theorem and then does the proof of boosting. So for this length of talk, on the technical side, I'll do the hardcore theorem stuff, but we'll revisit an open problem and a little bit of intuition at the end. So this might be a good time to ask any questions about boosting, if there are any left.
So just to check, this concept class depends, the concept class C depends on M and gamma.
Yes. Yeah, for every M and gamma, there is a C. Yes, that's the statement, yes.
Your statement's not so much about like boosting, so much as like separating weak and strong learning, right? And then that just implies there's no way to boost because.
Correct, yeah. So we focus on sample complexity, which has some pros and cons. The pro is you can get very strong statements like this, which imply that kind of no matter what your boosting algorithm does, you can't hope for anything stronger. The con is we're not viewing the booster as like an algorithm that black box calls a weak learner and constructs it in some way. It's more permissive, which is a pro.
That's what I'm saying. You're sort of just separating weak and strong learning.
Yes.
Rather than like really saying something about boosting, because boosting you would like to be efficient or something.
Yeah, so there'll be an open problem at the end, which is related to standard boosting, that we'll talk about this efficiency thing. But yes, you can view it stronger, weaker than a direct boosting statement, but yes, it is just about sample complexity of learning.
And you don't have a result of this type for the replace mix replacing smooth distribution with any distribution.
For there, 1 over gamma is tight. You can't prove a lower bound.
That was the set of the-
Yeah. So this separates, in some sense, separates smooth boosting and standard boosting. Yeah. Okay. Now we'll go to hardness amplification. So kind of in your mind, like total new context shift. I'll talk a little bit about the connection, but to start, this will be a little bit different. Okay. So hardness amplification is in some sense the opposite direction, some sense dual to boosting, right? So in boosting, you want to take an algorithm that learns to 51% accuracy, and then you create an algorithm learning to 99% accuracy. In hardness amplification, you start with something that's mildly hard. So it can't be approximated to 99% accuracy by poly-size circuits. And your goal is to create something that's very hard. Okay, so then it can't be approximated even to 51% accuracy by poly-size circuits. Okay, so very similar, but some sense the opposite direction. Okay, and the Yao's XOR lemma is a good example of this. Let me tell you a little bit about why you might care about hardness amplification. For de-randomization, it's often helpful to have very hard functions, those in which you can't get a guess much better than 50%. And so these hardness amplification results allow you to do de-randomization from, in some sense, less assumptions. You only need to assume weak hardness, which you can then even use less assumptions down the line. But the point is this hardness amplification, in addition to just being a nice fact about the hardness of functions, has other applications within complexity. And the particular result we will be interested here is Impagliazzo's hardcore theorem, which is, as Luca said, a very magical result just on its own. Okay, so what does the hardcore theorem says? As with all this hardness amplification results, we start with the assumption that F is mildly hard. And we're going to specify some size S circuits. So every size S circuits has at least 1% errors. And I want to visualize this as thinking about the whole domain, 0, 1 to the n. And you can think of, for every size S circuit, the blob of inputs you err on. And the point is, these blobs, we have no known connection between them at this point. They can just be disjoint blobs of size 1. Okay, that's what it means to be 1% hard. The hardcore theorem says there is a single impossibly hard set of inputs, a single blob of size 2% that, roughly speaking, condenses all the hardness into this tiny set. And the guarantee is that on this single hard set H, there is no small circuit that gets 51% accuracy. So sweeping an issue we'll get to in a moment under the rug, roughly speaking, this is as if all of C1, C2, C3, and so on all coincided on the same set, and all of their errors came within this small set. That's not exactly what happens, but that's kind of the message. Okay, so it's quite a nice result just on its own, and it has a.
It's amazing.
It is amazing.
The only explanation for hardness is an extremely hard small set.
Yes.
But
Yeah, it is magical. Thank you. And so we should be very interested in any results we can prove about this, right? Via proof. Okay. So So I'm going to tell you a little bit about the connection between the hardcore theorem and boosting, because that is kind of the underpinnings of this. A lot of the talk, we won't actually be directly talking about this connection because we'll just be proving our lower bound, but I think it's nice to see it. So you can prove the hardcore theorem from an appropriately stated version of smooth boosting, and you do it by contrapositive. So by contrapositive, you start with the negation of the conclusion. So you start by assuming over every fairly large set H, you can get a 51% approximation. Okay, and then what you do is you use boosting. The boosting algorithm is constantly choosing new smooth distributions, getting a 51% accurate hypothesis and combining them together. And H being large is exactly uniform of H being smooth. So you kind of do exactly what smooth boosting asks you to do, and then you combine these hypotheses into a single F that gets 99% accuracy.
maybe I should point out that this is earlier than Laval-Cervelli, or it's normally some proof of Russell Impagliazzo's hardcore theorem, which is in Russell's paper.
Ah, okay.
It's this game theoretic, it basically does.
I think Russell also had some note that.
It's not Russell, he acknowledges norm, but this is norm's proof. Russell's proof was iterative. Yeah. You can think of Russell also doing some kind of multiplicative way update. No, I mean this, game theoretic perspective. I mean, you use the min-max theorem.
But you need the minimax theorem.
Yeah, exactly.
In this one as well,
Saying,
yeah.
It goes back, it's already in
Yeah.
Russell's paper acknowledged by,
Okay, yeah, I'll find that and add it here. Yeah. Thank you. Okay, yeah, so you said, wait, no, Nissan?
Nissan, he's not an author. Once Russell, we were sitting in Russell's talk explaining this theorem. And then now came up with an alternative proof.
Which is this one.
And which is basically, which is like this one. It's not called boosting. I'm not sure boosting existed.
Yeah.
Yeah.
So any Nissan like private communication to Russell?
No, you look at Russell's paper.
He
He
said
has two proofs.
Okay.
One hit and one not.
The original paper.
The original paper.
Ah, okay. Great. Okay, so we have an even older version of this theorem. Okay. So these have been connected for a very long time, boosting and Hartford theorem.
Yeah, I think they named it, they in the paper learning is not mentioned at all and boosting it up. And Adam and Walker.
They named this.
Named,
I see.
made the connection to, to.
And I think there was also I could be misremembering, the Adam and Rocco paper had like different versions of smooth boosting, give you slightly different parameters. I don't know. Yeah, I don't know what parameters were known prior to that. Okay. Great, so these ideas have been very connected, and so perhaps it's not so surprising that when we prove a lower bound for one, we can upgrade it with a bit of work to a lower bound for the other. So, okay, yes, contrapositive gives you the hardcore theorem. Okay, so the main downside of the hardcore theorem, which kind of takes away from this message that all the hardness is literally a blob, but morally that's still true. So what's the main downside? You start with mild inapproximability against size S circuits. However, you end up with strong inapproximability, this impossibly hard set, only against size S prime circuits where S prime is asymptotically smaller than S. So when I call it impossibly hard, I'm cheating just a tiny bit. Okay, and you get the same sort of expression as you do on the boosting side. So if you want this impossibly hard set to be hard to even 1/2 plus gamma approximate, then S prime is gamma squared times S. Okay, and this is an inevitable byproduct of boosting style proofs. At least some size loss is. If you're creating a final hypothesis by combining many together, well, the circuit size seems like it should always increase. So you're going to need some overhead, but it's not so clear exactly what the right overhead is. And this question we found in a blog post by Luca in 2010. And then there was some work after Lu Tsai and Wu, which showed that certain classes of proofs needed this gamma squared. It's maybe slightly more general than just boosting, but kind of fitting within that same framework. And our second main result is that this size loss of gamma squared is necessary. And this is unconditional. It doesn't depend on how you prove the hardcore theorem. It just says that this statement needs a gamma squared overhead.
Here we don't lose the log factor.
Here we don't lose a log factor. The log factor comes up in learning. Maybe I'll mention a tiny bit there. Yeah.
So the hardcore theorem, I mean, one of the nice things is that it actually gives you a subset, right? Which is like a smooth distribution.
Mm-hmm.
But can you imagine like a pseudo hardcore theorem that gives you like a distribution that's like hard for like for small circuits, and then you need less boosting, like less.
You mean a distribution over sets, or just I'm not viewing a single set, but just some distribution that's
distribution.
Yes, I think they're equivalent. So some of the proofs find a smooth distribution, then you round.
I mean, not a smooth distribution. I'm saying like.
Oh, potentially not.
Smoothness. Let's like talk about the distributions.
So you mean you allow, perhaps requiring allowing the hardcore set to be very small, like.
You get the small set is a uniform distribution.
Right. The small set is smooth, but we're saying, you know, like if I remove this requirement for smoothness and I prove like a weaker hardcore theorem for you know, giving something that's even like smaller than what you'd call smooth, can you show that you'd need like for this type of thing you'd get like hardness for larger circuits? Like, is there some kind of trade-off?
Yeah, good question. No proofs I know get better than gamma squared, Our tightness here only holds for, constant size subsets, smooth distributions. I think there is a way of doing it that even gets it for the smaller ones, but not 100% clear. That gets the tightness, but the upper bounds, oh yeah.
It works only for your definition of smooth. If we wanted gamma to be one of a polynomial, we don't have.
Gamma being one of a polynomial, we still get, but H needs to be some constant size subset. If H is less than constant size, then we're gonna get some loss depending on what it is. It's some polynomial loss in the density. I don't remember exactly, it might be squared.
So this 99% you cannot get 1 minus 1 over polynomial.
Good, yes. There's often a delta in the hardcore theorem, where this 99% is 1 minus delta, and that is open. And I can point to later in the talk, we transform the problem into what to me seems easier, but I don't know the answer in that easier version. But yes, this is hardness in one of the two main parameters in the hard, or tightness in one of the two main parameters. Yes. Good question. Okay. All right, so formally, what we proved is there is some function, I'll call it big F here to distinguish from little f's that will be later, that is easy to weakly approximate on every large set H. So if you want to get 1/2 plus gamma accuracy on every set, you need on every large set. Here, large just signifies some constant size fraction. You need size gamma squared times some parameter s. On the other hand, if you want to get 99% accuracy, even on just the single set of the entire domain, you need size s. And here, as before, this holds for every gamma, every s, and big N is a function of m. Yeah. Actually, there might be some relation between gamma and s, but it's pretty permissive. So let's say if they're within polys of each other, it's definitely fine. I think there's some exponential gap that's okay, but I need to go back and remind myself. Okay, so the technical portion of this talk will focus on this result. Most of it, there'll be a little discussion of boosting. And this is, even though you can prove the hardcore theorem from boosting, we didn't find a clean way to prove that one of our results follows from the other. So we just proved the hardcore first, and then we do a little extra work to get boosting, our tightness for boosting. So we'll mainly focus on this one. You'll see almost a complete proof of it, just a few details that we have. Okay. So the first thing is we're going to need a circuit size lower bound and upper bound, but circuit size lower bounds are notoriously difficult. You could, depending on what circuit size lower bound you prove, you could potentially win $1 million. So we shouldn't try to prove a lower bound for an explicit function, but circuit sizes for random functions are very well understood. So that will be a key tool we use. We'll use upper and lower bounds on the size of a random function. The lower bound, a random function is with very, very high probability, requires a circuit of size 2 to the n over n. And that has a very simple proof I'll give in a moment. Any function can be computed by a circuit of size 2 to the n over n. That's not too difficult either, but there are a few tricks you need to get the right over n that I could not recreate right now, so it's not on the slide, but it's, if you see a reference of it, it's not too difficult either. Okay, and the lower bound is just a counting argument. The number of circuits of size s, here there's an assumption that s is at least n, but we'll stick in that regime. There are only 2 to the s log s circuits, and this is a somewhat naive counting argument. You just kind of write the structure of all circuits and count. You don't have to do anything fancy where you like cancel functions that are the same, you just count the number of structures. And the number of functions is 2 times 2 to the n. So if you want to compute 99% or even 0.001% of functions, you need 2 to the s log s to be 0.001 times 2 to the n. And so you get s log s must be roughly 2 to the n, and then you get the lower bound here. Okay, so a pretty easy thing. And now we have tight lower and upper bounds, which we're going to need in the end, so this will be a key tool. Our construction will not just be a single random function. We're going to draw k many independent functions, and I'll show you how to combine them in a moment. These functions will not be fully random. For technical reasons, it's helpful to assume they're balanced. So I draw them uniformly over all functions that output 1 as often as they output 0, exactly as often. I think the proof would go through without this, but it's just easier to reason about balanced functions. Okay, and now I'm going to define this big F, which will depend on these k little f's. And so big F will take n times k bits as input, which we can think of as k blocks, one for each f, each of n bits. We first compute those k many functions. This gives us k bits, and then we take the majority. So then we output 1 if at least half of these k functions output 1, and we output 0 otherwise. So this is the main construction we'll be analyzing. Okay, put succinctly, it's the majority of k functions in this briefer notation. And now we prove two things. Here, I'm going to replace gamma with 1 over square root k, just because it's easier to think about, but this is identical to the previous theorem. This big function f, no matter how you picked little f1 through little fk, is easy to approximate to 1/2 plus 1 over root k accuracy. Somewhat easy, size 2 to the n over n, so still kind of big, but smaller than the second bullet. On the other hand, if you want to get 99% accuracy, you're going to need a circuit of size k times 2 to the n over n. This is roughly maximal. Like you could fully compute every function and then combine them to get an upper bound of k times 2 to the n over n, and we prove a lower bound up to constant factors. Okay, and the intuition for these two results is pretty simple, and we're going to explore this intuition in the proof. So the intuition for the first one is it's enough to compute one block. And so we can use the loop enough result to compute one block with a size 2 to the n over n circuit. That intuition goes through pretty directly. The second intuition will be useful, but won't go through as directly, which is to get high accuracy, roughly speaking, you have to compute most blocks. Maybe not all of them, maybe you could ignore a constant fraction, but you have to compute a constant fraction of the blocks, which gives you this overhead of k. Any question here? Okay, and I'll go over a bird's eye overview of the proof. And the first is, I don't know how familiar the audience is with Junta complexity, so I'll define what Junta size is. But that will really answer why the majority function appears in our construction. It has some nice properties from the perspective of Juntas, and this will formalize the intuition. And we want to go from this to circuit size, lower and upper bounds. And for this, we'll use our lifting theorem. And I'll state the lifting theorem and discuss it a bit later, but it allows you to interpolate or go from Junta size to circuit size. In order to prove this lifting theorem, we're going to need something we call soft Junta size. It's not too complicated of a notion, but a slight generalization of Juntas. Okay, so a Junta is a function that depends on few inputs. So think of L here as something that's a bit smaller than K, or sometimes noticeably smaller, but just L is less than K. Okay, and a function is an L Junta if it depends on only L of its input coordinates. You can formalize this by saying there is some function that truly takes in L bits, and then L many coordinates, and the output of G on any k-bit string is just H on the corresponding L-bit string. Okay, so Juntas are a well-studied notion throughout theoretical computer science. From the perspective of complexity, they're a very simple notion of how complicated a function is that's easy to get your hands dirty with. So that's quite nice. You can often prove very strong things about Juntas. In learning and property testing, they have a particularly nice perspective, which is they correspond to feature selection. So if I have a machine learning model that perhaps has millions of features as inputs, but I want a simpler model, a Junta says, oh, instead of those million, look at 100. And the Junta, like you kind of want the best Junta, corresponds to the best selection of features. And so in learning and property testing, they're pretty well studied. But we won't actually need any of that. This is just some background on Juntas. Okay, so two things about majority that I have overflow slides if we want, but they're fairly simple, not too hard to prove. The first is that you can get a weak approximation of a majority by a one Junta on any smooth distribution. If instead of smooth, I said just the entire uniform distribution, this is a well-known fact, and the intuition is pretty simple. A one Junta could just be the first coordinate. And if I learn the first coordinate is a 1, it's a bit more likely that the majority of everything is a 1 than if I learned it was a 0. And this 1 over root k is exactly what you get when you do the analysis. It turns out that goes through for smooth distributions with a slight modification. you can no longer guarantee that the first coordinate is necessarily a weak approximator, but one of the coordinates is, in fact, just a uniform random coordinate will be a good approximator. And that's not too difficult to choose. Okay, and the second is if you want to get 76% accuracy, you need to learn half the coordinates. And kind of similar intuition here. If I learn half the coordinates, I have a pretty good guess of whether the majority is 1 or 0, but I might still be surprised by the second half. And this 3/4 comes from like, there's kind of a equal chance of surprise combined with like, you get 50% for free. So you kind of get half of the non-trivial stuff if you learn half the coordinates. Yeah, this is even on just the uniform distribution, this lower bound. And these two properties are all we need to know about the majority function for our construction. Okay, so I now want to formalize this intuition by defining a class of circuits that's very limited, which kind of allows us to directly use the intuition with no work. And then we're going to have to get rid of this assumption that we have this very nicely structured circuit. So we're going to say a circuit is hierarchical. If perhaps as the name suggests, it does things in the hierarchical way, like it wants to approximate this f, which has these inner functions f1 through fk. It chooses some of those inner functions, here it's choosing 3 of them, exactly computes those inner functions, and then combines them with f. So this is a pretty strong assumption on the circuit, but nonetheless, it's something you can define. And the thing here is if the fi are chosen randomly, then each one it wants to compute will typically require size 2 to the n of n. So the size of this hierarchical circuit is essentially L, the number of circuits it computes times 2 to the n of n. Okay, and this is like really just to directly take the junta stuff and translate it. So we have these two results about the junta complexity of majority. And the first result lets us say that we can always compute this big F by a hierarchical circuit of size 2 to the n over n, find the one block that gets a weak approximator and exactly compute it. And any smooth distribution here, it turns out will lead to any smooth distribution here as well. You have to show that, but it's not too hard. The lower bound gives you a similar result. If you want to 76 approximate majority via a hierarchical circuit, you need a circuit of size k times 2 to the n over n. This k is kind of a k over 2 secretly, but it all goes into the asymptotics, even on the uniform distribution. So I'm not claiming that the statement on the right is super interesting. I've made a very strong structural assumption that essentially just says the junta size is small and large, but the point is we can get rid of this assumption. So on the upper bound side, it's easy to get rid of this hierarchical assumption because if you have an upper bound for a hierarchical circuit, that's just a type of circuit. So you have an upper bound for circuits. Our lifting theorem says you can get rid of this hierarchical assumption on the lower bound. So proving a junta result gives you a lower bound against all circuits. And this should be a little bit surprising. Okay, let me tell you the formal statement of our lifting theorem. There's a lot of notation here, but intuitively it says if you prove a lower bound against juntas, it translates to a lower bound against circuits, where what we really mean is to give me any function g, think of g as a majority function, it is hard to approximate by a junta. Now draw f1 through fk independent and randomly amongst balanced functions, and consider the composed function g with each of these f1 through fk. Then if you want to get a similar approximation, we lose a constant factor here, then you need a circuit of size L times 2 to the n over n. Essentially, the naive thing where you just choose L blocks and fully compute them is optimal, assuming you pick k random functions.
Like all the lifting theorems in communication complexity.
Yeah.
Sorry for that.
Yeah. I mean, really cool how you can go from juntas to circuits, because I think of juntas as one of the simplest things, and circuits as maybe the most complex thing to analyze. So I found this a little surprising, but all the randomnesses will be helpful. Yes, and there was an earlier question by Avi about the delta factor. Here we have constant delta, so we start with 99% hardness, but sometimes you do the hardcore theorem where you start with 1 minus delta hardness, and delta is a parameter. This result says it would be enough to prove tightness of the hardcore theorem for juntas with that delta factor, but I don't know how to do it. So you could get the circuit result by just improving our understanding of junta complexity. I'm not actually sure if I believe delta should be necessary for room to observe. It's
No, you're using just the Punta result for 76% or whatever.
yes,
But there are final theorems of this type which are what's called it ain't over till it's over theorem.
yeah,
It's called the conjecture of de-escalation. You have the majority function, and I have to see 99.9% of the, or 99.999% of the bits, and ask you what the majority. Or I let you see 1 over root n of.
Mhm.
You're almost all there. So of course, your confidence in the value of majority improves, but they say it ain't over till it's over. Means that
yeah, good name.
you know the final, that there's still a chance that you don't know the majority.
Majority itself would not be enough for our purposes because the amount of additional coordinates you need is only a constant factor. So to get 76%, you already need k over 2 coordinates. If you get k, you get 100%. Then it's finally over. So to prove tightness for room to complexity, we need a function where as you get closer to 1, the Hunta size increases asymptotically. I don't know if there's another example of something like that. That also needs to satisfy the upper bounds.
If you look at the parameter.
Okay, yeah. Is it majority specific or in general?
Yeah, but majority, it's like voting, it's like a vote, random vote. That's a concept.
Okay, we won't prove this version of the theorem in this talk. It uses a bit of Fourier analysis. It's not super difficult, but I thought the special case we need here is more intuitive and I think better for a talk setting. So we're going to handle the special case when the number of coordinates you need to know is linear in the total number, which by the way is satisfied by the majority. So this special case is sufficient for our purposes.
Presumably in your theorem, like the fact that the functions are like random is very important.
Yes.
Just pick ones that are, say, 2 to the n over n hard.
It is very important that they're random, and this brings up something I wanted to say but didn't. This would not hold if they were all the same random function. So maybe that gives you.
Well, sure, yeah, but.
Yeah. So yeah. So like
There's like ones that don't agree or something, or.
I don't know of a property other than they're just fully random with high probability. Fully random.
Like you could do something where you like can't compute all of the outputs with less than, I don't know, like 2 to the n over n times k.
Yeah.
Because it's all the same function, you can compute all of them with 2 to the n over n instead of 2 to the n over n times k.
Yeah, there's Uhlig's mass production theorem, if this is something that it lets you do this sort of thing for the same function. Yeah, I don't know of nice properties that would suffice, except one thing is this is an approximate thing. So even if you tell me to like exactly compute all k bits, I need k times 2 to the n over n, like the kind of the direct product. It's not clear that that translates to something like this, where we're happy with approximations. So yeah, I don't know. Yeah, go ahead.
Is this true just for any class like that's small, instead of just
Like for
class of small circuits? Yeah.
good. Basically, what we need is that the counting argument is typed for a class, which holds for many classes. You'll see the proof of this version. So something similar would hold for many other classes of functions.
You're saying like that you can interpolate any set of points with some complexity. Anyway, never mind. I'll just see what happens.
Yeah. It's going to be a counting argument in the end. So this 2 to the n over n comes from their S to the S circuits. So if you had like a different counting argument, then you get a different but related lower bound for a different class of functions. Okay. All right, so now we have kind of the whole sketch. We know why we chose majority. It has nice properties from the complexity perspective, and we know where we want to go. We just have to prove this Lipton theorem. And once again, I'll define a class of circuits. In order to define soft Hunta size, I'll first define a class of circuits that is a little bit more broad than hierarchical circuits, but doesn't quite hit all circuits. We'll call these hierarchically valued circuits. And the name perhaps suggests what they are. We say a circuit is hierarchically valued if the input-output behavior aligns with some hierarchical function, but we make no assumptions about the internal structure. So there are some f tilde 1 through f tilde k, and some outer function h, such that on every single input, 100% of the time, the output of the circuit aligns with what you would get for h composed with f tilde 1 through f tilde k. But we're making no assumptions about the internals. For example, it may be useful for the circuit to like share some computation as it goes between the blocks. Okay, and we want to prove a lower bound against these. So the key to doing so is there are roughly speaking 2 steps. The first step is to say, and I'm just going to write majority. So for the lifting theorem, you can replace majority with any hard Hünte function, but I write majority to be clear about what we're talking about. So for majority, if a function of this form is to approximate the majority function, it must be the case that most of the blocks have a good approximation for the blocks used in the majority. Okay. And the second step is that this is very unlikely with randomness of f. That once you fix a single c, it fixes f tilde 1 through f tilde of k. We're not really going to look at h. We're just going to look at these k functions. And the probability that a constant fraction of these are well correlated to their corresponding counterparts is going to be small enough for us to then prove that this is so unlikely you need a lot of circuits. And if you need a lot of circuits, you need a lot of circuit size. Okay, so it will be helpful for this first one about many blocks being somewhat correlated to define what I'm calling a soft Hünte. A soft Hünte is a randomized function, but you can think of it as some generalization of standard Hüntes. So it's defined by an outer function h and a correlation vector, which we're taking every correlation between 0 and 1. And okay, let me tell you actually the roughly speaking, and then we'll go to the definition. Roughly speaking, any coordinate that's a 1, the soft Hünte fully knows. Any coordinate that has correlation 0, the soft Hünte does not know at all. In correlation between 0 and 1, it has some guess about what the coordinate is, but not too much. What it receives is when it wants to compute on input x1 through xk, what we say is it gets a bit that is correlated for each xi, it gets a bit yi that's correlated to it. So if the correlation is 1, yi equals x, and it knows it. If the correlation is 0, yi is uninformative, right? Regardless of what x is, yi is just a random coin toss. And it smoothly interpolates in between. So the soft Hünte, it knows the correlation vector. It can use the correlation vector when deciding the function h, and it's trying to use the information it has in the best possible way.
Can we interpret this as a noise operator on a normal?
Yes, I think that's equivalent. Yeah. But there'll be a notion of size afterwards, and I think you could define the size with like noise plus regular Hünte, but it'd be a little weird. Where like the noise kind of like decreases your size, but Hünte, yeah. And there are variants of this you could define. This one tends to work quite well here. And it will be helpful to have a notion of size. And we're going to use the expected number of coordinates you know. If all the alphas are 0 or 1, we have just defined regular Hüntes, because the size will be the number of coordinates you know, every other coordinate you don't know. But in general, this could allow you, maybe it's better to know 2 coordinates 50% of the time than to just know 1 of them fully. Maybe you can get a slightly more informative guess of what the output is. Any questions about this definition? Okay, 2 key claims about soft Hünte size. The first is that it's related to Hünte size in the sort of way we need, which is if you prove that every L Hünte has epsilon error on some function of interest like majority, then every L over 2 soft Hünte has at least epsilon over 2 error. And the proof here is pretty straightforward. This is the step that you would need a stronger version of to prove the whole lifting theorem. But for the linear case, this analysis suffices. By Markov's inequality, the probability you know more than L coordinates is at most 1/2, right? On average, I know L over 2. It's unlikely I know more than L. And if you condition on knowing less than L coordinates, the best thing you can do is put a Hünte down. So the best thing you can do is get epsilon error. This analysis here, you're assuming kind of a lot of power to the soft Hünte. You're assuming that it knows what coordinates it knows. But even that version is enough to prove a lower bound. That's enough for this version of the theorem. Does that make sense? Okay, and the second is a pretty simple extension of Shannon's bound. If you fix any single function f and draw f uniform balanced, it's very unlikely that you have a constant size correlation. So on average, you know half the bit. On average, F tilde and F agree on half the coordinates or on half the inputs, it's unlikely they agree on say 60%. And it's the unlikeliness is it's like exponentially small, 2 to the minus or double exponentially small. And this result, it's not hard to prove. If you didn't say balanced, this would be Hoffing's inequality, right? You can whether you correlate on every input would be an independent bit, an independent coin flip, and so you could just apply a standard tail bound. For the balanced case, you just need like a tiny bit more work, and you get something like this. But this essentially says that like it's roughly speaking as hard to get a constant correlation as to fully fit F, which will be nice for our purposes. Okay, and now we're ready to understand these hierarchically valued circuits. So we start with any such circuit. We only know its input-output behavior, so that's all we'll write down, these F tilde and this outer function each. And then we draw this big F uniformly from our process. And we want to say that the probability that C 90% approximates F is exponentially small in K and 2 to the n, which combined with Shannon's counting argument is going to exactly get to the sort of lower bound we want. Okay, we already said majority is hard to 76% approximate. So we lose a factor of 2 in the error. So 76 would go to 88, but I'm just rounding to 90 for who's on the slide. We need a K/4 sawtooth to 90% approximate the majority function. In order to get a K/4 sawtooth, that means that the average correlation over the blocks is 1/4. It means at least 10% of the blocks have to have at least 10% correlation. You can kind of, the worst case otherwise is that 10%, 9.9% of the blocks have 1% correlation and the rest have 9.9%, and that won't get you to K/4. So this is not too hard to show that there must at least be a constant fraction of the blocks, like a constant correlation. And here as well, the full lifting theorem can't use this kind of simpler argument. And now we just do a fairly simple probability bound. So there are, K choose 0.1K choices for the indices. Once you choose those indices, the probability that they're all have this constant correlation, well, each is exponentially small in 2 to the n, and there are 0.1K of them, which here, if K is reasonable relative to n, such that this term doesn't have a huge effect, you get 2 to the minus K times 2 to the n probability. Just what we want to show. Okay, so this gives us a lower bound against all hierarchically valued circuits. Okay, and now we need to go to full circuits, which might seem like a big step, but in this case, it's actually pretty small. It'll follow by triangle inequality. So we want to prove that there is no circuit. The probability any circuit 95% approximates a random F is exponentially small in K and 2 to the n. Okay, and this will imply our lower bound that with very high probability, you need a large circuit because there aren't too many small circuits. Okay, and we'll do a visual proof here. So fix any such C, no assumptions about it at all, and consider the ball of all things that it 95% approximates. If there is no F of this form in this ball, then we're already happy. Then this probability is 0. So that case we're done with. We can assume that there is at least one function of this form that it 95% approximates. So fix that function. Now draw the 0.1 ball around this function, and triangle inequality, it must fully contain this 0.05 ball. And so we now are going to show that this big ball, if we draw a random F, is very unlikely to fall within this larger ball. So it suffices to show for an F star that is the majority of K functions, the probability you 90% approximate a random F is exponentially small in K and 2 to the n. Okay, I went through that a little quickly. So are there any questions about this? It suffices to show or any of this in general? Okay. And now I think we're done because this F star is a hierarchically valued circuit, right? It has some inner functions F. It even has the majority on the outside, which we didn't use, but we could have if that made our life easier. And so it's unlikely that a random function falls within. Okay. Yes, and then we get the tightness of the hardcore theorem for this mostly random function with a little bit of structure using our lifting theorem. Yeah, which potentially gives you ways to prove tightness of other regimes of the hardcore theorem if you can prove better results about this. Okay, yeah, that was all I wanted to say about the hardcore theorem. So any questions before I close with a little bit about boosting?
So do you require your capital F to be balanced as well? I mean, it will be almost balanced, but it won't be.
No,
Won't exactly be balanced.
we do not require capital F to be balanced. If K were odd, I think it will be balanced because the majority is balanced, but if K is even, then yeah, it will be exactly balanced.
So it's given the hardcore size exactly, whatever, 2 delta, if delta was the, you get the factor 2 in this proof.
So this gives you a lower bound against any constant size. So it's, I think the factor of 2 is impressive on the upper bound side. When you like kind of prove the hardcore theorem, it's impressive to large sets. When you prove a lower bound, I think it's impressive to prove a lower bound against smaller sets, and this is any constant size set.
You're talking about the size of the hardcore.
Yeah. Is that the factor of 2 you're talking about?
Yeah, factor 2 is the best you can hope for.
Yes, on the upper bound side.
Yeah, if you have a circuit with error probability 1 minus delta, you cannot hope for bigger than 2 delta.
Right, because it like encompasses all of the hardness.
Right.
This proves a tightness for hardcore sets that are of that size and slightly small. This proves you couldn't get a better hardcore theorem if instead of 2 delta, 1 delta was enough for you, for example, or 0.01 delta.
Good.
For constant delta.
Yeah. Right.
Okay. Closing thoughts about boosting. Okay, I want to tell you just a little bit more about this boosting proof, in particular the concept class, and it should look very similar to the hardcore theorems. We define the concept class, where you pick any k balanced functions, and you take the majority of them. In other words, our construction on the hardcore theorem side, to do it, you just pick a random function from our concept class. And this is not so much a coincidence, we reuse a lot of the analysis, so that's why we use essentially the same construction in both pieces, but we don't quite reuse all of the analysis. Okay, and for this concept class, and m being 2 to the m, we show you can 1/2 plus gamma approximate it with m samples, sorry, not approximate it, learn it, over any smooth distribution. And if you want to get 99% accuracy, you need m over gamma squared. Here we do lose a log factor. And I'll say a tiny bit about this log factor, but more importantly, let me just say like what goes through easily and what doesn't. So it turns out the tightness for the hardcore theorem really easily gives you this lower bound, which is nice because I typically think of lower bounds as harder than upper bounds, so we can reuse maybe the harder portion of the proof. And the intuition here is our proof of the lower bound for the hardcore theorem. We showed that these f's, like this concept class, has a lot of very well spread out functions. And having so many spread out functions means you need a lot of circuits to cover the whole space. And it turns out that that notion of the functions being very spread out translates really nicely into sample complexity lower bounds. So that goes through quite easily. In this case, the upper bound does not go through so directly. If you recall, our upper bound for these says that you can just fully compute one coordinate, one block. But in learning, you're not going to get enough information to fully compute one block. Instead, each sample, roughly speaking, gives you a little bit of information about all the blocks. So you have to argue that we can kind of combine these little information about all the blocks into one hypothesis that is a weak learner. And here we do lose a log. So I'm showing the log here, but maybe be slightly more accurate to put an O tilde of m here and then make this one not a log. This is kind of exactly the hardcore theorem. This one, there's a log loss. So yeah, I won't go into this argument here just for time purposes. But it does require a little bit more work. Okay, and I want to close with an open question about actually standard boosting, and this goes into some of the earlier, like the time complexity questions. So I said earlier that this 1 over gamma is tight for standard boosting, and formally what that means is it's pretty easy to show that if I have a concept class and I can 1/2 plus gamma learn it with a m sample learner, then using m over gamma samples and get 99% accuracy. And you prove this by bounding the VC dimension. And you can also show this is tight for the concept class consisting of all functions. Okay, so this is different from smooth boosting, but it's not too hard to show. However, all known time-efficient boosters lead to a 1/gamma² sample complexity overhead. So the question, and I'm going to formalize it in kind of a general sense, is if I have a concept class and you promise me it can be efficiently learned, weak learned, 1/2 plus gamma accuracy with M samples over all distributions, can it also be efficiently strong learned with 99% accuracy using M/gamma samples? And I'm not sure whether I believe this should be true or false. For an upper bound, you could perhaps imagine some sort of booster that like looks at its sample, like learns some things, calls a weak learner on some overlapping things. Not so clear to me, but maybe it's possible. Lower bound, you're of course gonna have to make some assumption, some complexity assumption about time-bounded learners, but you know, I think feel free to assume crypto or whatever there, that would be helpful. But yeah, I don't know whether I believe it or don't believe it, but I think it'd be nice to know. Okay, that's it. Thank you.
Great questions.
So the question of learning efficiently, I should think of C as a class over 0, 1 to the n, and you like polynomial time.
Yeah, I think that's that's the most, I would say, the easiest setting to formalize this question in. Yeah. But you could, so you could either do that where 0, 1 to the n and efficiently means poly n, or you could just ask for this time to be related to that time for some t. I think either one would be interesting. Yeah.
It's not the problem that your M is 2 to the n to begin with. Right? So efficient in 2 to the n would be inefficient.
For my concept class, I think you can like do something where it's just define out a subset of the bits.
Yeah, that's cheating, guys.
Yeah, it's not really, yes, I agree. So I think there's, but that's for the lower bound. So an upper bound here, maybe it would work in reasonable parameter regimes, not just like this 2 to the n thing. The advantage is we have kind of here we have this 2 to the n thing. So.
Yeah. Also in the outgrowth theorem, your S is exponential size. So
and you can also
cheat.
But yes.
You can pet.
Yeah, exactly.
But,
I wonder if there's a nice way
to functions like your.
I don't know if there's a super nice way to formalize a not cheating version, because you can always do like smarter padding where you just like take the parity with a bunch of extra bits and now you're not really a junta. So I don't 100% know how I would try to formalize what a non-cheating result would look like. But morally, yes, this is cheating. It's only for the first
You want hardness of amplification for, I don't know, factoring.
Yes.
Right. I mean, maybe
for specific functions.
Factoring, 1% of the one.
Yeah, definitely for specific functions is one way to not cheat.
You don't really handle situations where you have a natural polynomial size algorithm.
Yes.
Approximates it to 90.
Yeah, I mean, it's random functions are not nice, which is what to be used. So, yeah.
More questions?
Yeah.
I don't really know how the boosting algorithms work, but I remember you got some papers saying that like you can subsample data and then reuse samples that way. Would that such a thing be useful for this open question, or the parameters bad for that?
Good. Yes. So subsampling is a procedure that could sometimes be useful. So I have a larger data set and I draw random subsamples of it, and then I kind of use some smaller algorithm on it. It's feasible that sort of algorithm could work with standard boosting procedures, but I don't see how that. I don't think that work would give you an easy analysis of how to do so. But that is an example of something you could do here. And subsampling, it's not just my work. It's actually for pack learning to get if you know the VC dimension, to get the very best sample complexity without there's some log factors that if you want to get down, one of the ways of doing it is you run ERM, like the standard given as data set, find a hypothesis with 0 error. You subsample your data a bunch of times, find a bunch of these 0 error things, and then combine them with the majority. So that sort of idea has been used in learning, and it is something you could try. I don't see how to analyze that.
I think, Peter, in these cases where you subsample, the initial data set has to be larger. Your M would be the size of the subsample.
Yeah, but it is larger. It's M over gamma, right? So
Yeah, exactly.
M subsample, I don't know, you could like 1/gamma² subsamples the size M and run the algorithm. I don't, that's.
Yeah. You also, I wouldn't expect to just uniformly take a subsample because the boosting is reweighting things. But
Right, yeah.
maybe you subsample and you reweight just enough. I don't know. There are things you could definitely try. But yeah, it'd be interesting.
All right, thanks.
Thank you.